Okay, once you know the chain rule, you can apply that to finding the derivative of inverse functions. So here, let's consider in general a function and then its inverse. And for the sake of simplicity in writing here, it would be easier to keep things straight. If we call the inverse function g and the original function f. So the function and then its inverse, knowing that g represents the inverse function. Well, if we take f of g, so we do the composition of a function and its inverse, we just get the original variable, x, right? That's what an inverse means. If you put x into the inverse and then you take the function of the inverse, then you just get x back out. Or you flip that process and you take the function of x and then you take the inverse of that, you just get back to x. That's how inverse functions operate. So knowing that and knowing the chain rule, we can take the derivative of this composition. And how does that work? Well, we have from the chain rule df dg and then multiplied by dg dx. And dg dx would be the derivative of the inverse. And because f of g of x is just equal to x, we know what this derivative has to be. It has to be equal to 1 because the derivative of x is 1. And so to solve for the derivative of the inverse, we do 1 divided by the derivative of the original function. But being careful here, this is the derivative of the function with respect to g as its argument. So when we do this, we will do df dg, plugging in g as its argument, and then substitute in whatever the formula is for g. So we'll see that in the next example. Right, this is just the textbook writing this out. I think it doesn't add anything to go through the details here, but this is how your textbook writes out using the chain rule to find the derivative of this inverse, and it also calls g the inverse function. So this is the derivative of the inverse, 1 over the derivative of the function, where g is its argument. All right, so to our example. Let's say we have the function x squared. Obviously, the inverse operation is the square root. So we have the square root as the inverse, x squared is the function. It doesn't really matter which one you look at as the inverse and which one you look at as the function. It works both ways. If a function is invertible, you can call either one the function and either one the inverse. So in this case, we're saying the function is f and its inverse is square root of x. And we know that f of g of x means plugging in g of x for the argument of f. So we take g of x and we stuff it in place of x. So f of g of x is really just g of x squared. And g of x is square root of x, so we have the square root of x squared. It takes a little while to get comfortable with, changing the variable names here and, putting g of x in for just x. That may be uncomfortable, might not feel right doing that. But remember, what's in the argument of a function is just a placeholder. This could be anything. It could be a picture of a dog. And this would be the picture of the dog squared, whatever that means. So x doesn't mean it has to be x. It's just whatever happens to be in here, you take the square of it. So if it's f of g of x, you plug in the whole thing of g of x in for its argument. Okay, doing that composition gives us x as we expect for any inverse function. We also know from the chain rule that the derivative of this composition has to be equal to 1. And so we can apply that to these specific functions. So df dg is going to be 2. So now we're saying this is g and not just x. This is now g. Let me get my laser pointer like that one better. This is now g. So if I do df dg, I have a power relationship I bring down to, and it would be just 2 times g. But then we have to remember g actually means something. G means square root of x, so this becomes 2 times the square root of x. So df dg is 2 times the square root of x. And then what is dg dx? That's what we want to know. That's the derivative of the inverse. That's the derivative of this square root. And so dg dx equals 1 divided by 2 times the square root of x. And so now we have the derivative of the inverse using the chain rule, using the fact that the composition of a function and its inverse just gives you x. Now, interestingly, we haven't really talked about how to take the derivative of functions that have non-integer power. So if it was a 2 here, we know that you bring down the 2 and you subtract 1 from it. What if it's not an integer power? What if this is just any other rational exponent? Well, let's just try the power law rule and see what happens. So let's assume that the power law works. If I were to take the derivative of this function, I would bring down the power, so you get a half out front, and then subtract 1 from the power. A half minus 1 is minus a half, so you'd have 1/2 times x to the minus 1/2, which is the same. This thing here is the same as 1 divided by the square root, because a negative power means you could put it in the denominator as a positive power. So this is 1 over 2 times the square root of x, which is just what we found using the inverse theorem. And what this shows, or at least it supports the idea, that the power law rule extends to any rational exponents. It works for a half, it works for a third, it works for 2/3, it works for any rational exponents that are there. You don't have to have a specifically integer power for the power law to work. So from the textbook, there is a rule stated extending the power rule to rational exponents. If you have a rational exponent, it can be written as 1 over n or m over n. You can use the power law rule just as it's written. Bring down the power, subtract 1 from the power. There's your derivative. So nice little benefit of the inverse rule is we were able to prove or show. We didn't prove it kind of for every case, but we showed that it works for any exponents. Now let's take a different example and just look through it here to see how the process might work. And this is more to show that it works. This isn't necessarily how you would find the derivative of the inverse of this function, but just to show you that it does work. So let's start with the function, and the function is x over 1 minus x. First step is to find the inverse, and so that means solving for the other variable. So if y equals x over 1 minus x, we want to have an expression that is x equals some function of y. That would be the inverse operation. So start by cross multiplying 1 minus x to both sides, so minus 1 minus x times y, and then 1 minus x over here will cancel the denominator. And so on the left we have 1 minus xy equals x. Then the next thing I would do is put everything involving x together. We need to combine those together so that I can then separate it out and isolate it. So y is left behind on the left, and on the right we add the plus xy. So we've added plus xy to both sides. Then I can now factor out the x, and when you factor out the x, you're just left with 1 plus y. And now last step, I can divide by 1 plus y to get x by itself, and now I have the inverse to this original function. So if y is equal to x over 1 minus x, then x is equal to y over 1 plus y. Okay. So we have the inverse function. If we want to write it as a function of x, which is the standard practice, you just switch the identification of x and y. And what that is really saying is that the domain of the original function becomes the range of the inverse function. The range of the original function becomes the domain of the inverse function. So our inverse function is now g of x, x over 1 plus x. So I just replaced y with x and x with y. Okay, so I've written those two functions up here. This is the function, this is the inverse function. And now let's find its derivative. So let's find its derivative. So what is the derivative of this original function? It's a quotient. We can use the quotient rule. We could also use the chain rule here, but I've just done this with the quotient rule. So we have 1 minus x in the denominator. So we have the bottom times the derivative of the top. The derivative of the top is just 1, so 1 minus x times 1. And then minus the top times the derivative of the bottom. So x, now the derivative of the bottom, this gives you 0, this gives you a minus 1, so you just have minus 1. And then on the bottom we have 1 minus x squared, the denominator squared. So we're leaving that alone, but then we can simplify the top. 1 minus x times minus 1, minus minus gives us plus. So 1 minus x plus x is just 1. That's our derivative for the original function. What about the derivative for the inverse? We can use the inverse theorem. So now that we have this, the derivative of the inverse is 1 over the derivative of the original function, so 1 over this, and then replace x with g. So it's 1 over 1 over 1 minus g squared, which is the same thing as 1 minus g squared. 1 over anything is just the anything. Okay, so this is the formula that we used here. dg dx is 1 over df dg. That's our inverse theorem that we've learned. Okay, so now that we have g, we can plug g in, and 1 minus x over 1 plus x squared, you can do a little simplification. The way I did this was 1 can be written as 1 plus x over 1 plus x. Then they have common denominators. 1 plus x minus x is just 1. So we get 1 over 1 plus x squared. So we have the derivative of the inverse using the inverse theorem that we learned earlier. Now, the other way we can find the derivative of this inverse, if we have the function, is just take the derivative of this using the quotient rule, just like we did from the original function. So I just want to show that this works and you get the same answer both ways. So let's take the derivative of this using the quotient theorem. So we do the bottom times the derivative of the top, right? So 1 plus x times 1, and then minus the top times the derivative of the bottom. The derivative of the bottom is also 1, so just minus x. So 1 plus x minus x gives us 1, and then on the bottom we have the denominator squared, 1 plus x squared. So which is just what we found before. It works. In this case, if you know the inverse function already, the quotient rule is a simpler way to go about this. Actually, you need to know the actual inverse function either way. So in this particular case, the quotient rule is simpler, but we see that it works both ways. Whether you use the inverse theorem or whether you calculate the derivative of the inverse should give you the same answer. It should work for any functions that have an inverse. Okay, so we will use this when we get to exponentials and logs. We'll take advantage of this inverse theorem to show you how you can find derivatives of the exponential and logarithms.